Okay, welcome everybody to the TOC Colloquium. Just as a note, today's talk is being recorded for the FODSI YouTube channel. So if you don't want to appear on YouTube, keep yourself muted and your camera off. We're delighted to have Sanjoy Dasgupta joining us from UCSD. Sanjoy has made major contributions in algorithms and theory of machine learning. In particular, he's going to tell us about a recent exciting line of work on interpretable ML. So Sanjoy, over to you.
Okay, thank you very much. So I've been thinking about interpretable machine learning for the past 2 or 3 years, and it's a really exciting area for theory work. I think that there's a lot of new algorithmic and statistical problems to be solved here, and I'll talk about 2 little examples. So the first is interpretable clustering. And by the way, feel free to ask questions at any time. You could just type it into chat or just blurt them out either way, okay? So clustering, right? So this is one of, the age-old forms of unsupervised learning. And it's something that's widely used to understand a very large data set by simplifying it to just a few representative groups. Okay, so for example, a newspaper that say has tens of millions of readers might want to get a handle on who these people are. And one simple way of doing that is just by clustering them according to their reading patterns. And maybe it'll emerge that they're just 20 or 30 coherent groups. Okay, and that really gives some insight into the client base. So similarly, it's used a lot in understanding genes, products, transactions, and so on. And in all of these kinds of applications, it would help a lot if the clusters were easy to understand. Okay, so for instance, in the newspaper example, if one of the clusters was, oh, these are the people who primarily read the sports section, something like that. If the clusters was simple. Now, this is not, however, what clustering algorithms actually give us. In the case of hierarchical clustering, in fact, the clusters are really just pretty arbitrary subsets of data. And even the more well-behaved clustering algorithms, the best you can really hope for are convex regions of space, which are not very understandable in higher dimension. Okay, so let's look at K-means clustering as an example. This is possibly the most popular clustering algorithm of all time. And so you give it your data points, you tell it how many clusters you want, that's K, and it returns K cluster centers, which I've shown here in red. And now each point in space is associated with its closest center. And so the clusters are these Voronoi cells, these convex regions. Now in 2 dimensions, this is pretty understandable. But in higher dimension, it's hard to get a handle on what these clusters are, simply because the clusters are defined using Euclidean distance. And so you kind of have to keep all the features in mind, and there could be hundreds or thousands of them. So it's hard to sort of fathom the clusters, okay? It's not easy to think of a quick fix to this situation. So I'll talk about some recent work in which I was involved, where we proposed a sort of an interpretable version of K-means clustering. And I should say that, all the real work was done by these people here, Cyrus Rashtian, who is a fantastic algorithms person, is currently working at Google. Michal Moshkevitz, who is at Tel Aviv University and is working on theoretical foundations of interpretability. And Nave Frost, who is at eBay Labs in Israel, working on interpretable NLP. So here is the setup that we looked at, okay? So you've got this data set. You call your favorite K-means algorithm, your favorite K-means heuristic, and you get back a reference set of centers, mu1 through mu_k. And as usual, the clusters themselves are these, arbitrary convex regions. Now you want something interpretable. So you try to approximate these clusters using a decision tree. So in this case, for example, there are 5 clusters. And so what you would want is a decision tree with 5 leaves. And you can see that over here, you can actually do a pretty good job, okay? So the first split in the decision tree produces this cluster over here, which is a pretty good approximation to cluster number 2, okay? And so on, okay? So in this particular example, the original clusters are well approximated by the decision tree, and the decision tree is much simpler to understand. Each cluster is just a conjunction of a few thresholded features. So the question is that, can you do this more generally? You know, so maybe in 2D it's possible. What happens in higher dimensions, say, you know, where these convex regions can be a little bit more strangely shaped? Can you really approximate them well using these nice boxes, using these sparse hyperrectangles based on just a few features? And so let's go ahead and formalize the problem. Okay, so there's a data set X, and now the K-means cost of a particular set of centers is the following. For each point in the data set, you look at its closest center and you look at the squared distance to its closest center. And now you sum this up over all the points in the data set. Okay, so the K-means cost is literally the quantization error induced by replacing each point by its nearest center. Now, these clusters are too complicated for us. So instead, we just want a decision tree. And the decision tree will have K leaves. Each leaf defines a cluster. Otherwise, we can use the same cost function. So each leaf is a cluster. And so for each data point, just look at the leaf it falls in and look at the square distance to the mean of the leaf, okay? And so that is the corresponding cost of the tree, of the clusters defined by the tree. Now, because the tree is so much simpler, there's the danger that the cost of this clustering might be much, much higher than that of the reference K-means clustering. Okay, we can think of this as the price of interpretability. How large might this ratio be? And needless to say, you can define the same thing for the K-medians cost function. In this case, we're looking at L1 K-medians, where it's exactly the same, but instead of squared L2 distance, you have L1 distance. So in order to understand this ratio, we just looked at a very simple heuristic for actually constructing the tree, okay? It's a top-down decision tree construction algorithm. So we start with all the points in a single cell, that's the root of the tree. And now in this case, we have 5 centers, so we know we have to split it. Okay. And the way we do that is just by trying all possible splits. Okay. There aren't that many of them. If there are D features and N data points, there are really just N times D splits to try. Okay. And so we try all of these, and we pick a split that separates off at least one of the centers, but other than that, makes the fewest mistakes possible, okay? Where a mistake is when a point gets separated from its reference center. And so this first split over here makes only one mistake. There's this data point here, which has got separated from its center, center number 4, and instead is now teamed up with center number 1, okay? So on the right over here, we have just one center. We don't need to split it any further. On the left, we need to split again. And again, we try all possible splits. And in this case, we make 2 mistakes. Okay, these 2 points should have been with this center, but are now with one of these. We don't know which one it's really going to end up with. We don't know which center they'll end up with. One of these 3 guys. Okay, and then we split again, and we split again, and then we get a tree. Okay. And so over here, at the end of the day, we have a pretty good approximation. We've made a few mistakes, okay? But overall, it seems pretty close to the initial clustering. Okay, so here is the algorithm again, okay? So you'll start with a set of reference centers, and the way you build a tree is in this greedy top-down manner. You have a single cell containing all the points. And then anytime there's a cell that contains 2 or more of the reference centers, you split it. You try all possible splits and you choose the one that splits up at least one center and makes the fewest mistakes possible. Okay, and so at the end, you get k leaf cells, each containing one of the reference centers. It turns out that the cost of the tree can be bounded as follows. It's the cost of the reference clustering times 2h plus 1 in the case of the k-medians cost function, or 8hk plus 2 in the case of the k-means cost function. And here h is the height of the tree. So h is something between log k and k. Okay, so in the worst case, the blow up in k-means cost is by a factor of k squared, regardless of the dimension. So let me go into the proof of this. It's very simple, so I'll just go through it in its entirety. Okay, how are we able to bound the cost of this tree? So I'll show the proof for k-medians. The proof for k-means is basically the same. Okay, so we're building this tree, and at any given point we have some cell, okay, that we need to split. So here's a cell over here. U is an internal node of the tree. And it's got a bunch of data points and it's got a bunch of centers. In this case, there are 4 centers, so we know we are going to need to split it. Okay, let B of U be the bounding box of these centers. In particular, the cut that we choose has to separate off at least one center, so it's going to have to cut this box. Now, let diameter of U be the diameter of this bounding box. Okay, and since we're talking about L1 distance, it's just the sum of the side lengths of this box. Now, we're going to pick the cut that makes the fewest mistakes, that separates the fewest points from their correct center. Okay, and so let T sub U be the number of mistakes we make. We know it's not possible to make fewer mistakes. Okay, so these are some numbers associated with this particular cell. And what you can show is that the cost of the tree is at most the cost of the reference clustering plus the sum over all the internal nodes of the tree of the number of mistakes made at that node times the diameter of the centers at that node. Okay, and so let's see why this is the case. So this is an upper bound on the cost of the tree. So the reason for this is that, well, look at any data point X. It ends up in some leaf. If it ends up in a leaf with its correct reference center, we're all set. There is no additional charge for that point. If it ends up with the wrong center, well, then it got split from its correct center at some point. So there was some internal node of the tree that contained X. Okay, so it had some point, let's say that's X. It contained the correct center for X. Let's say this is the correct center for X. But then the 2 of them got split. So the split might have been something like this. Okay. And so at that point, so X was one of the mistakes made in that cell. It was one of the T sub U mistakes. And at the end of the day, X ended up in a leaf with one of these other centers. So the additional cost because of that is at most the diameter of these centers, is at most this quantity diam of U. Okay, so the additional amount that we have to pay for X is at most diam of U. And so summing over all such X, the additional charges for points are given by this term over here. Okay, so for each point that gets separated from its correct center, we incur a charge for it and we pay the charge at the internal node at which the separation occurred. Okay, great. So we have this upper bound here on the cost. What is this term here? You know, how can we bound this thing? Well, what we can show is that if suppose that instead of looking at the entire summation over the entire tree, you just limit attention to one level of the tree. In that case, this term is again bounded by the cost of the reference clustering. Okay, so if you limit attention to a single level of the tree, then the summation is at most twice the cost of the reference clustering. And since the tree has height h, what that means is that this term over here is at most 2 times the height times the cost of the reference clustering. Okay, and that's how the height comes in. And that explains this bound over here. Okay. Okay, so the one thing I need to explain now is this. So you look at any level of the tree, and you look at the nodes over there, and for each node, look at the number of mistakes times the diameter of the centers. That's upper bounded by the cost of the reference clustering. Okay, so in order to show that, I'll show something a little bit more specific, which is that if you look at any internal node of the tree, then the cost of the points inside that cell with respect to the reference clustering, so the optimal cost of those points, is at least the number of mistakes times the diameter of the cell. And then that would immediately imply this, because then we just sum over all cells at a given level. Okay. So let's see why this is the case. So we pick any cell, okay? And we want to show that if you look at the L1 distance between each point and its reference center, okay, assuming the reference center is in that cell. If not, we don't have to worry about it. That cost is at least the number of mistakes made times the diameter of the centers, okay? So to see this, pick any coordinate. We're going to split along some coordinate. Pick a coordinate, let's say coordinate I. And we know that the split we make is going to separate off at least one of the centers. So the split is going to be something like this. Okay, it's going to be one of these. It's going to be something along these, something between this first center and before this last center. We can imagine the centers ordered along this coordinate. And we know that the minimum possible number of mistakes is T sub u. So no matter how we cut, we're going to make T sub u mistakes. And so let's try a few specific cuts, okay? So let's look at a cut between the first two centers, this cut over here. And let's look at a cut between the next two centers. And let's look at a cut between the next two centers. Okay, so let's look at these candidate cuts. And we know that for each of these candidate cuts, there are going to be at least T sub u mistakes, okay? So for example, for this cut over here, we're going to make at least T sub u mistakes. T sub u points are going to be separated from their reference centers. Okay, and so for example, this might be separated from this, and this might be separated from this. So for each of these points, if we look at the interval between the point and its reference center, so the interval, this interval over here, that interval covers either this half or this half. It's got to cover one of those two halves. Okay. And likewise with this cut over here. If a cut is made over here, there are going to be T sub u mistakes. And if you look at those mistakes, if you look at the interval between each point and the center from which it was separated, it's going to cover either this half or this half. Okay. So now, if we sum over all points in the cell, okay, and we look at the interval between each point and its center, if we add these up, we know that either this or this was covered T sub u times, and either this or this was covered T sub u times, and either this or this was covered T sub u times. And so when we sum these up, the sum has to be at least T sub u over 2 times this entire length, times the length of the bounding box of the centers along the ith coordinate. And so now we just sum over the different coordinates and we get this result over here. Okay. So that's the proof for the K-medians case. And if there are any questions, feel free to ask. For K-means, it's much the same. Essentially, the same argument works. over here, we had to use the triangle inequality. And so for k-means, you use a 2 approximate triangle inequality. And over here, we had to sum up these intervals. And if you're doing this for k-means, you're summing up squares. And so you have to use Cauchy-Schwarz. And that introduces another factor of k. Okay. So, so this was published last year. And since then, there has been a whole bunch of other work improving these results, okay? By Laber-Murtino, Charikaran, who Makarichev and Shan have 2 papers on it, and a couple of other groups, okay? And there's a lot of overlap between these, but some of the highlights are, first of all, some randomized algorithms that don't even need to look at the data. They build the tree just using random cuts based on the centers, okay? What's also been clarified is that the interpretability ratio for k-means is not k squared. It's better than that. It's something between k and k log k. And finally, the most exciting result of all, in my view, is due to Makarichev and Shan. And they show the following. So what they say is that suppose you just keep growing the tree. So instead of stopping at k leaves, you keep going until you get to 2k leaves, okay? And now you still compare to the k-means clustering. So it's like a bicriterion thing. If you do that, then the interpretability ratio drops from k log k to just log squared k times log k, okay? And so that's a dramatic improvement. So let me just give a brief sense of how some of this goes. Okay, and I'll just very briefly. As I said, there's a lot of overlap, but just by way of example, let's look at the paper by Esfandiari, Mirokni, and Narayanan. Okay, and what do they do? How do they get the interpretability ratio down to k log k instead of k squared? So what our scheme was is that when we want to split a cell, we just pick the cut that makes the fewest mistakes. And we found that if we do that, then the resulting approximation ratio is k times h, where h is the height of the tree. And in the worst case, this could be k squared. That's what we found. But when you look at that, you think that, wow, you know, this would be nice if this was k log k. And is there some sort of balancing that you can do to make that happen? And so what they say is, you know what, let's use a different greedy criterion. Instead of picking the cut that minimizes the number of mistakes, pick the cut that minimizes the number of mistakes divided by how many centers go to the left and how many centers go to the right. And if you do that, then the approximation ratio is indeed k log k. Okay. So it's a better greedy criterion. Now, interestingly, in order to analyze this, they need to show that there exists a cut for which this is not too large. And the way they do that is by the probabilistic method. And they said, in fact, if you just pick a random cut, this won't be too bad. Okay. So what this implies, though, is that there is a randomized algorithm that doesn't look at the data at all and that has the same expected interpretability ratio. Okay. Okay. Okay, so let me just show you a couple of experiments just to see how these things pan out. And, you know, kind of the high level thing here is that, as is the case with many approximation algorithms, the factors observed in practice can be much, much smaller than those that appear in the bounds. Okay. So there are lots of lines over here. Most of them are for competitor schemes. So you can just focus on the black lines, okay? So over here on the left, this is the cover type data set where there are where we ask for 7 clusters. And you can see the interpretability ratio, the cost of the decision tree is very close to that of the reference clustering. This next one is the 20 news groups data set. And again, it's the same thing. This last one is CFAR10, which is images. This one's harder because the clustering is being done in pixel space, which is a little strange. And here, the ratio is something like 1.25. But if you grow the tree a little more, okay, that's if you have 10 clusters. If you grow the tree until 20 clusters, it drops some more. And if you grow it until 40, it drops down to 1.15. Okay. So the take home here is that in the case of
Sanjoy, what happens in CFAR 10 if you don't do the clustering in pixel space, if you do some kind of reasonable embedding? I guess to maintain interpretability, the embedding itself has to be somehow interpretable. But
right. Yes, so
it looks like your numbers were noticeably above 1 for CFAR 10, like 0.2.
That's right, yeah.
I wonder if it gets better if you embed in a space where the clustering is, more linear anyway.
Yeah, so I think that would be a great experiment to do, just to figure out what happens if it's embedded in one of these standard neural net feature spaces, something that just makes more sense for images, maybe even just histogram of gradients or something like that.
Sorry, we have a question in the room.
Hi, thanks for the great talk so far. I guess I'm not fully convinced that this tree model is actually interpretable at all, because if you compute decision trees in practice, they actually turn out to be very unruly and hard to look at. For example, why is it interpretable if we say we have multiple branching points on the first coordinate, right, in level 1 versus level 50? That's not really interpretable, right? If we're branching off on the first coordinate 10 times in various different parts of the tree.
Yeah, so right, so depending on the type of data and on the size of the tree, there are varying levels of interpretability. But I think it's a big step up from what Kmeans gives you. So it's something that's closer to being understandable.
Okay, I see.
That's all I meant. It's an improvement.
I see. Okay, cool. Thank you.
Yeah, so the take home is that these decision tree clusters are easier to understand than the original clustering. And most of all, it's algorithmically very easy to get a tree like this. And the loss that you incur in K-means cost is quite modest in both theory and practice. Okay, so I think an open question here is, what about other types of clustering? And I think a prime candidate would be hierarchical clustering, because those really are probably the worst offenders when it comes to lack of interpretability. Okay, in a hierarchical clustering, the splits are fairly arbitrary. And so it would be nice to come up with an interpretable version of that. Okay, so I've talked a little bit about clustering, and now I wanted to talk about classification. So, as I think we all know, machine learning classifiers are increasingly being used as part of decisions that really affect our lives. Who gets hired, who gets a loan, who gets parole, who gets policed, all of this kind of stuff. And it's a little bit scary because, as we also know, these classifiers are far from infallible. They make plenty of mistakes. And in fact, if you run them on data that's different from the training distribution, who knows what they're going to do? And perhaps worst of all, I think that the technology for confidence assessment, for knowing when they should abstain, is still in a pretty primitive state. And so for all of these reasons, for accountability, it's important to have understandable models. Okay, so what kind of models are understandable? And this is, of course, something that is tied up with the vagaries of human cognition, and a lot more work has to be done in cognitive science just to get a better characterization of, what are the kind of models that we understand well. But in the meantime, there seems to be at least a partial consensus on certain types of models that are pretty understandable. And these include short decision trees, very sparse linear models, and simple exemplar-based models. And by that, I mean, think like nearest neighbor with just a few prototypes. Okay, so why not just use those if those are understandable? And the problem is that they might not be the most accurate models, okay? So what are the most accurate models then? And, I'm not a practitioner, so it's not a question, it's not something, that's not a matter on which, I can speak with any kind of experience. But what I can do is to just echo a common sentiment that is also reflected in, Kaggle competitions and so on, which is that for tabular data, the most accurate classifiers are often things like random forests or boosted decision trees, whereas for sensory data, they're often things like neural nets. Okay, and so what is this? What is this tabular versus sensory? So the way I think about it is a tabular data is something like, like a medical record or something, where each feature is like the person's age or temperature. Each feature is a morsel of information. It's a solid chunk of information that tells you a little bit about the label, maybe just a tiny bit, okay? On the other hand, in sensory data, you have something like an image, where each feature is a single pixel that essentially tells you nothing about the label. Okay, it's not a morsel of information, it's like a crumb. And the only way you get information out of these crumbs is by basically integrating them into morsels. And that's what neural nets are very effective at doing, convolutional net in the case of images, or a transformer in the case of text. Okay, so it's sort of a morsels versus crumbs distinction. Now, unfortunately, all of these are basically inscrutable, okay? And that's bad news for interpretability. So the next question is, well, okay, so they're better, but how much better? And here, one person who's done really great work is Cynthia Rudin. She has basically been doing fantastic work on interpretable ML for the past decade and a half. And what she's done is to really just look at one application after the next and show that a sensibly chosen decision tree is often almost as good or just as good as some of these more inscrutable models, and yet are so much more interpretable. Now, what we wanted to do is to do something a little bit different, which is to say, well, what if we just go beyond decision trees to something maybe a little bit more expressive? And so I'll show you what I mean. So over here, and so the models we're going to talk about are sets of decision rules. So over here, I have shown a decision tree, and I don't know if any of you recognize this, but this is the classic decision tree from 1972 that Leo Breiman and Jerry Friedman and colleagues fit on data from the UCSD Medical Center. And here, so what they were trying to do is the following. So when a heart attack patient is discharged from hospital, are they at risk of dying within the next 30 days? Because if they are, maybe they shouldn't be discharged. And so they collected some data and they built this decision tree. It just asked 3 questions: blood pressure, age, and something related to heartbeat. And the doctors just loved it, okay? Because the variables being used are highly relevant, and yet the doctors by themselves would never have been able to come up with the correct thresholds. Should the blood pressure threshold be 91 or 95? Should the age threshold be 62 or 65? Who knows, Nor would they have been able to come up with the right way to sequence the questions. And so this little decision tree was just pure gold. Okay, it's a real sort of example of just the beauty of these simple interpretable models. Now, in this case, you can think of this tree as being 4 rules, okay? A rule at each leaf. So the points that arrive in this leaf are basically classified using the conjunction of 3 features. And the points that arrive here are classified using the conjunction of 1 feature. Well, if we're happy with conjunctions of 3 features, why don't we just allow rules that are just an arbitrary set of rules that are conjunctions of three features. Okay, so just to kind of loosen things up a little bit, okay, just a collection of rules of this kind. And for example, it's no longer the case that every rule has to contain the feature at the root. Okay, so it's more flexible. So these are the kind of rules we'll be looking at. And basically each class is specified in disjunctive normal form. Okay. And so I'll be talking about some recent work, which is still under submission with Bill Lin and a couple of his students, in which we use DNF for understandable classification. Now, is DNF even learnable? So there's plenty of bad news on it, actually. But I like to keep a sort of a positive mindset. So let's not worry too much about that. Then there's also some good news. And in fact, at the end of the day, computer hardware people solve very large DNF learning problems routinely. It's called logic minimization. And in our case, I guess one way to think about it is that we want relatively short conjunctions. There aren't a lot of them. Okay. And so it's really a sort of set cover problem. It's not that crazy. Okay. So, what do? We binarize the data. Okay. So if it's real value to threshold at multiple points, one hot encoding. So now you have this binary data with labels, and you apply your DNF learning heuristic, and it crunches it down to rules that are consistent with all the training points. This part is not problematic, but we run into a big issue. And the problem is that you have overfitting. So in these tabular data settings, there's often a lot of inherent stochasticity. And I'll just define what that means very soon. But the result of that is that you end up getting lots and lots of rules that are much too complicated and do not generalize well. Okay, so what do? So you start, so here was a very simple fix. You start with the data set, and now you use it to learn an intermediate classifier. And the only purpose of this classifier is going to be to denoise the data. Okay, it's because it serves no other purpose. It doesn't have to be interpretable, but in fact, it has to be chosen very carefully, and I'll talk about that soon. Now you edit the data set. You toss out any point whose label disagrees with this intermediate classifier, and then you do DNF learning on the edited data. Okay. And this seems to work rather well. And I'll just show you a quick example, and then we can talk about denoising, which is the really important part. Okay. So here is the cardio data set. Has about 60,000 points. There's a lot of stochasticity in this data, so there's no hope of getting a perfect classifier. Using DNF learning only, the accuracy is something like 66%, nowhere near the best possible. A boosted decision tree is much better with 73%. But after denoising, the DNF learner is better. And so, and just to see examples of rules, on the original training set, which is 56,000 points, this is one of the rules that you get. It's a conjunction of 4 features, not too complicated at all. But it's a highly specific rule. It applies to only 14 training points. The denoising removes 25% of the data, so it really throws out a lot of the data. And now this rule goes away. And instead, you get a much more general rule, which just uses, in fact, one of these features and covers over 15,000 of the training points. Okay, so a lot of the initial rules were overly complicated just to address the noise in the data. Okay. Okay, so what do we mean by noise? And what do we need for denoising? And so by noise, what is meant here is inherent stochasticity. And so let me just explain that. So let's say that all the data points are medical records. Okay, so this is somebody's medical record, and this is somebody's medical record. And you want to predict whether they're going to get a certain disease in the next year. Now, given a person's record, it is not deterministic whether they're going to get the disease or not. 2 patients with exactly the same record, one could get the disease and the other doesn't get the disease. There's stochasticity. okay? And so at this point, for this record, it might be the case that there's an 80% chance, 80% of people with this record end up getting the disease in the next year, okay? So we would like to predict 1, okay? However, a training point over here could easily have the wrong label. There's a 20% chance that that point will have a label of 0. Likewise, over here, for this medical record, there might be a 45% chance that the person will get a disease in the next year. In that case, we want to predict 0, since that is the more likely outcome. But a training point, this training point could easily have the other label, okay? And so that's the notion of noise here. It's just inherent stochasticity. Now, the other thing I wanted to point out is that the decision boundaries themselves can be arbitrary. Okay, this is not a linear situation or anything like that. The boundaries can be anywhere. Okay, so this is the setting in which we are. And there's a standard way of formalizing this. So you have a data space, you have the label space 0, 1. You have a distribution from which all data come. That is the sort of fundamental assumption of statistical learning, that there's an underlying distribution from which everything, past, present, future, comes. And now there's this inherent stochasticity. At point X, the label could be 0 or 1, and the probability that it's 1 is given by this function eta of x. So we want to learn a classifier, and we want a classifier with low error, where the error is just the chance that it's wrong. In many of these situations, it's not possible to find a classifier with 0 error. But the best possible classifier is the Bayes optimal classifier. And it's the classifier that predicts 1 if this conditional probability is greater than 1/2 and predicts 0 otherwise. You can't do better than that, okay? So getting back to logic learning, what we really want to do to denoise the data is to take the labels we were given and replace them by the Bayes optimal label. Now, unfortunately, we can't do that because we don't know the Bayes optimal label. We don't know this classifier. So instead, we learn some surrogate classifier and use that instead, okay? So what are the properties that we want from this classifier? So first of all, it should be consistent. As the amount of data grows, it should converge to the Bayes optimal error rate. And second, the thing we want is that it's going to make some mistakes. The mistakes should ideally not be spread out all over the space, because we're covering the space with these nice rectangles. We don't want to contaminate those rectangles. We want the errors to be localized near the boundary. And so the picture is something like this. We have some arbitrary decision boundary. We are going to make errors because we have a finite amount of data, but we want the errors to be near the boundary. We want the errors to be something like this. How do you do this? Okay. And to do this, I'll talk about some work that I did with my wonderful colleague, Yoav Freund, and with Shai Moran and Akshay Balsubramani. Okay. So, so by the way, Sam, roughly how much time do I have?
Well, we should let people go at the end of the hour. It would be good if there were a few minutes for questions, but we've also taken a couple of pauses for questions. So, you know, if you want to take 10 minutes, that's fine. Does that sound reasonable?
Sure. Okay. Thank you. Okay. So we're now in the setting of non-parametric classification. We want to learn a boundary, and the boundary is completely arbitrary. There is inherent stochasticity, which is captured by this eta function. The best possible classifier is the Bayes optimal. We're going to choose some non-parametric classifier based on the points we've seen so far. We're going to call it G sub n. What are desiderata for this classifier? So the first thing we want is consistency, that as the amount of data goes to infinity, we converge to the Bayes optimal error rate. But in fact, we want a little more. We want universal consistency, which means that this holds without any assumptions on this. For example, we do not need this to be continuous. Why? Well, first of all, because we can't check these kinds of assumptions. And secondly, because the whole thing with non-parametrics is that you want to fit whatever the data is, no matter how crazy it might be. Okay. And so in the 70s, people saw that this was possible, and it was a huge revelation. And since then, there are quite a few methods that have this property of universal consistency. Now, we also need rates of convergence, but here we run into trouble because in non-parametrics, it is not possible to give distribution-free rates of convergence. It's not possible to say, after seeing n points, your error is going to be at most 1 over square root n. And this is because this eta function can be arbitrarily spiky. And the spikier it is, the more data you need, okay? So the rate of convergence does depend on the distribution. The usual way around this is to make smoothness assumptions, is to say, well, let's just say this is Lipschitz, or it satisfies some Holder property, and basically to boil the problem down to 1 or 2 smoothness parameters, and then give rates of convergence in terms of those. So this is standard practice, but it's also not very great because it gets rid of all the interesting structure in the problem on which the rate of convergence really does depend. It actually makes a lot of different algorithms look the same, even though their behavior is very different. It's a very, very tiny lens through which to view quite a complicated scenario. But what can you do? How can you give a rate of convergence without smoothness assumptions? And okay. So I'll talk about k-nearest neighbor, or at least start with that, because this has a lot of nice properties. But the real problem here, so in k-nearest neighbor, you look at the nearest neighbors in the training set, the k-nearest neighbors, and just return the majority label amongst them. The problem here is how to choose k. Okay, so look at this data, it's on the line. The data is on the line. Over here, high chance of 0 label. Over here, high chance of 1 label. And over here, it's a little closer to a half. So for these points here, you want a small value of k. Your nearest neighbors will be on the same little ledge. If you take a higher value of k, you end up averaging in these other things, which will give you the wrong label. But over here, you want a much larger value of k, because if you have a small value of k, like 2 or 3, the points are so noisy that even an average of 2 or 3 points is not good. And so k really needs to be different for different points. And so this is our estimator over here. So what we do is that in order to predict at a certain point, we grow a ball around it. And let's say we get 10 training points in the ball. So we say, what is the majority label? Is there a significant majority of 1? If so, predict 1. Is there a significant majority of 0? If so, predict 0. Otherwise, keep growing the ball. And you just keep growing the ball until the training labels in the ball have a significant majority. The minute you get to the majority, you predict that label. If you never get a significant majority, then you predict the don't know label. Okay. So it's a very simple classifier that chooses the number of neighbors adaptively. And for this classifier, you can show some very strong properties. So first of all, you can define a very simple notion of margin for this case. Now, margin, we are sort of used to from linear separators, where it's just a number like the buffer zone around the separator. But in the non-parametric setting, a margin is simply an easiness score for each data point. So for every point in space, the margin is how easy that point is, okay? And it's very simple to define something like this. And it turns out that the rate of convergence you can give is something of the following form. As soon as the amount of training data exceeds 1 over the margin of a point, you will predict correctly, okay? So, and this is a completely assumption-free thing, no smoothness or anything like that. Each point has got its margin, how easy it is. As soon as the amount of training data exceeds 1 over the margin, you get that point correct. This in turn implies universal consistency. And if you have smoothness, then you can show that the difficult points, that is the one with the points with very small margin, are in fact the points that are very, very close to the decision boundary. And that's one way of thinking about the errors being localized. Okay. So, and so this is the denoising scheme we used. Okay, so this is an example of a non-parametric estimator where you can give rates of convergence that are actually meaningful, where you haven't just swept everything under the rug using one or two smoothness parameters. Okay. And it gives you, therefore, additional information about the points that you will get right and wrong. Okay. And then it's reassuring because it shows that the errors will be localized. Okay, so I'm not going to have time to get into the definition of margin. It's quite straightforward, but I'd be happy to discuss that later. So the take-home message here is that we probably shouldn't be too scared of learning DNF. You know, there are things that are hard about it, but you know, it's not that frightening, I think, overall. The main difficulty here is denoising the data first. And we've suggested one particular way of doing this based on an adaptive nearest neighbor scheme for which we can give you know, very interesting rates of convergence that don't rely on smoothness parameters at all. Okay, so I'd like to finish by just thanking my various co-authors.
Thanks. Thanks, Sanjoy. I guess that's the end of that's your last slide, right?
Yes, that's it.
Yeah. Okay. Good. Yeah. Thank you for the lovely talk, Sanjoy. We have a few minutes for questions before we have to let everybody go to Thanksgiving. So questions. Go ahead and unmute yourself, or we'll moderate if it gets really crazy.
Hi Sanjoy, could you explain the margin?
Sure, yeah. Absolutely. So here's the margin. So what is the margin at a particular point X? Well, let's say that X should have a label of 1. That means that the conditional probability at X is greater than 0.5. We'll say that X is P gamma salient if there is a ball around X of probability mass P, such that the average label in this average eta value in this ball is at least a half plus gamma. And what that means, and that if you look at any smaller ball, the average value is at least a half. What that means is that if you get 1 over gamma squared points in this ball, you will correctly predict the label of X. Okay, so if you get 1 over gamma squared points in this ball, you get the correct label of X because the bias is a half plus gamma. And in order to get 1 over gamma squared points in this ball, the overall number of points you need is 1 over P gamma squared. So the margin at X is now the supremum over all P gamma squared for which this point is P gamma salient. And so it's something that is really very attuned to nearest neighbor. It really captures the rate of convergence of nearest neighbor. So you can give a rate that doesn't depend on any assumptions. And in order to show that this implies a universal consistency, what you need to show is that all points have positive margin. And that follows, that's just true in Euclidean space. And in fact, in any metric space that satisfies the fundamental theorem of calculus, that you know, the derivative of the integral is the value of the function, you know. So any finite dimensional normed space, and you know, some doubling spaces and so on. So yeah, so that's the notion of margin.
Thank you.
Thanks.